Refrigerators and heat pumps. Can we reverse a Carnot engine and make a refrigerator? What do we mean by reversing a heat engine? In a reversible heat engine, all the processes are reversible. This means that an infinitesimal change will reverse their direction. So we look at the heat rejected, QC, from a heat engine. If we change the temperature of the heat engine by an infinitesimal amount, the direction of heat transfer will change. QC will become a heat input, which the engine takes from the low temperature, TC. Similarly, we can reverse the direction of QH, the heat input. An infinitesimal change will mean that it is heat rejected to the high temperature, TH. Finally, we can reverse the work done. So instead of getting work from the system, we will now supply work to the system. The heat engine now becomes a refrigerator. We define a refrigerator as being any device that takes heat from a low temperature region, that transfers it to a high temperature region, and is supplied with work. How, in practice, does a refrigerator work? A liquid absorbs latent heat during evaporation and yields it while condensing. Now, the temperature at which the phase change occurs increases with pressure. So we can choose any temperature we want for the phase change by adjusting the pressure. The working fluid in a refrigerator is typically a liquid that boils at a temperature much below 0 degrees C. We boil the refrigerant at low pressure and low temperature, and we condense it at high pressure and high temperature. The inside of a refrigerator is the low temperature region at temperature TC. There's an evaporator coil inside the cabinet of the refrigerator. Low pressure refrigerant passes through this evaporator coil. Heat is transferred to the refrigerant as it changes from liquid to vapor. The vapor is compressed to a high pressure and temperature in a compressor. The saturation temperature to which it is compressed is well above the temperature TH of the ambient air. The vapor passes through the condenser coil, which is on the exterior of the refrigerator, and it loses heat to the surroundings as it condenses. We can build a two-phase Carnot refrigerator between the low temperature heat source, which is at temperature TC, and the high temperature heat sink, which is at temperature TH. We select the pressure of the evaporator so that the saturation temperature in it is just below TC. We therefore get a heat input, QC, from the heat source into the fluid in the evaporator. We get a two-phase mixture coming out of the evaporator, and this is now compressed isentropically until it reaches the temperature TH. Work is supplied to the compressor to drive it. We select the pressure of the condenser so that the saturation temperature is just above TH. Saturated vapor goes into the condenser and it loses heat to the heat sink at temperature TH. Saturated liquid comes out of the condenser. This is now expanded through a turbine and fed back into the evaporator. The work from the turbine is taken to drive the compressor. If we place a box around this device, this is a Carnot refrigerator. It takes heat QC from the heat source at TC. It rejects heat QH to the heat sink at TH, and there's net work supplied to this. The performance of a refrigerator is defined by the coefficient of performance. This is defined as being the heat removed from the low temperature, QC, divided by the net work input, W net. From the first law, we know that W net is equal to QH minus QC. The coefficient of performance, therefore, is QC divided by QH minus QC. Simplifying that, we can write it as 1 divided by QH by QC minus 1. We can now do an entropy balance for the refrigerator. The change in entropy over a cycle is equal to the change in entropy during the heat addition minus the change in entropy during heat rejection, and this must equal 0. The entropy change during heat addition is given by QC divided by TC, and the entropy change during heat rejection is QH divided by TH. Rearranging that, we get that QH upon QC is equal to TH upon TC. The coefficient of performance of the refrigerator, therefore, is equal to 1 upon TH by TC minus 1. Since TH is greater than TC by definition, the coefficient of performance of a refrigerator must always be greater than 0. Typically, the coefficient of performance is greater than 1. As TH approaches TC, the coefficient of performance increases. In the limit that TC goes to 0, the coefficient of performance goes to 0, which means that the work required to drive the refrigerator, W net, becomes infinite. We can therefore say that cooling a volume to absolute 0 using a refrigerator requires an infinite amount of work and therefore is not possible. So we can never achieve absolute 0 inside a refrigerator. If we do an energy balance on a refrigerator, we know that W net, the work supplied to it, equals QH minus QC. Since TH is greater than TC, that implies that QH is greater than QC. Therefore, W net has to be greater than 0. We have to supply work to a refrigerator to have it operate. This is summarized in the Clausius statement, which says that it is impossible to build a device that operates in a cycle and transfers heat from a low temperature region to a high temperature region without work being done on the device by the surroundings. This is an electrical heater which is supplied electrical energy, W net, and it dissipates that in an electrical resistance, generating heat QH, which it supplies to the high temperature region at TH. We know from the first law that QH must equal W net. Now suppose we used instead a refrigerator and rejected heat QH. In a refrigerator, QH would be equal to W net plus QC, the heat taken from the low temperature region. This is what we would call a heat pump. A heat pump is a device that takes heat from the cold exterior of a building and rejects it to the warmer interior. And we can show that this is a more efficient use of energy than simply dissipating it in an electrical heater. The coefficient of performance of a heat pump is defined as being QH, the heat rejected, divided by the work supplied to it, W net. From the first law, W net is equal to QH minus QC. Substituting that in an expression for the coefficient of performance, the coefficient of performance equals QH upon QH minus QC. And we can rewrite that as 1 upon 1 minus QC upon QH. Using our entropy balance, we know that TC upon TH is equal to QC upon QH, and therefore the coefficient of performance of the heat pump is equal to 1 upon 1 minus Tc upon Th. Since Tc upon Th is less than 1, the coefficient of performance is greater than 1. Typically for a heat pump, the coefficient of performance varies from 2 to 3. The heat supplied by a heat pump is therefore significantly greater than the electrical work input. It is therefore more efficient to use a heat pump to heat a house than to use an electrical heater. To summarize, a refrigerator is a device that takes heat from a low temperature region and transfers it to a high temperature region while being supplied with work. The Clausius statement is that it is impossible to build a device that operates in a cycle and transfers heat from a low temperature region to a high temperature region without work being done on the device by the surroundings. Reversing a Carnot engine gives a Carnot refrigerator. The coefficient of performance of a refrigerator is 1 upon Th by Tc minus 1. The coefficient of performance of a heat pump is 1 upon 1 minus Tc divided by Th.